All right, this is going to be the video for the first part of chapter 20 for AP statistics, which is about hypothesis testing. And right now we're considering just data that's categorical so we can find a proportion of yes cases. All right, so let me present the whole screen here and we'll go through mostly the notes and we'll end up working the first problem in the practice packet. So if you can have that available on your calculator, that would be helpful. All right, chapter 20. First of all, let's review that we know that there are three different levels of inference, right? We have the population level, which is what we're studying. And if we have categorical data, we have some no's, some yeses, and P is the proportion, which is the proportion of the population that's yes. That's a parameter, something that parameters go with populations, so something we're trying to study. But we take a sample from the population and we study the sample and then we infer things about the population. So in the sample, we have a percentage that are yes, and that's p hat. That's the statistic that's calculated from the sample that's estimating the corresponding value in the population. And then we know based on chapter 18 and the fact that we know that p hats vary according to a certain model, we can predict based on the sample size how much variation there's going to be from p hat to p hat value. If you do the sample multiple times, we can have a sampling distribution model for the sample proportions, and that will allow us to determine various things about that. Okay, so three levels of inference. There's the population with its parameter, in this case a proportion p, and then there's the sample with its statistic p hat, and then there's the sampling distribution model that shows how p hats would vary from sample to sample if we repeated this many times. Okay, so in chapter 18 we were concerned about the idea that we just wanted to figure out how things behaved at the sampling distribution model level. So we pretended that we knew the population values, the population p-value, and from that we could figure out that there's a formula for the mean. The mean of the p hats aligns with the actual proportion in the population, and the standard deviation is given by the square root of pq over n, right? So we have a specific formula for determining how this behaves based on the sample size. Okay, that was all in chapter 18. And for us to do those calculations, we had to know the proportion values in the population, but we don't really typically know that. So this is kind of fantasy land, what we were doing in chapter 18, right? Because if we knew that value for the, the population, we wouldn't bother to do this taking a sample thing. Okay, in chapter 19, we acknowledge the fact that we don't actually know this p-value from the proportion. We just have our p hat value. And so we went ahead and calculated it with the formulas down here, but when we use the sample value, then the standard deviation is now called the standard error, okay? And it's probably similar to the proportion to the real value, but we know that this p hat is moving around a little bit and it's not the actual value, so it's not perfect. And because of that, then the one value we have that's an estimate for p is the p hat, the proportion of yes in the sample, right? But we have to put an error boundary around it, plus or minus the margin of error, to create a confidence interval. So we can say we're saying 95% confidence that this true population percentage yes value is somewhere within this interval around what happened in our actual sample. So that's what chapter 19 was about. It was about taking the sample's value but bounding it with a confidence interval, a margin of error, and trading off confidence level for precision here. Okay, in chapter 20, we're going to go back now to centering things at the population parameter value. But because we don't know that value, we're going to make an assumption. We're going to assume what the population value is, and that assumption is called a null hypothesis. Okay, and then we're going to take whatever happened in our sample, and we're going to compare that to a normal distribution centered at our null hypothesis value and determine how unusual would it be for this p hat value to happen if the value we assumed for p it was correct, right? And we're going to basically say that but by determining how far this is away from how many standard deviations we are away, we might at some point say, well, this is unusual, or maybe we conclude it isn't unusual. And we're going to be able to determine based on whether the sample is unusual whether we can trust our assumption, our null hypothesis assumption. Okay, so we're going to be using the likelihood of p hat happening if we assume a particular value, and then use that to judge whether or not our assumption is correct. Okay, that process is called hypothesis testing, and that's the subject for chapter 20. Okay, so what is a hypothesis? A hypothesis is just a working assumption. It's something that we believe might be true about a situation, but has not yet been demonstrated. We then look at the data and we see if the facts are consistent with the model that's proposed by that hypothesis. All right. So the first really important thing to know is, can we prove a hypothesis is true using data? And the answer to that is no. In statistics, NAP statistics, there's no way to prove that a hypothesis is true. Okay. What we can do, though, is we can consider the facts that we have from our sample. If those facts are consistent with a hypothesis, we can believe the hypothesis is probably true, but we haven't proved that it's true, right? On the other hand, it might be easier for us to say if the facts are inconsistent with the hypothesis, we can be very confident that the hypothesis is false, which means we can reject the hypothesis. So it turns out that it's much easier to disprove a hypothesis than it is to prove it. So we only use data to try to poke holes in hypotheses, to disprove hypotheses. Let me give you a simple, crazy example. Let's say that I made the hypothesis that all cars are red. Okay, to try to prove that, that would be very difficult because we would have to look at every single car that has ever been made in the entire world and verify that every single one of them is red, right? That would be very hard to do, right? On the other hand, if I say, well, what's the opposite of that? What is the opposite of all cars being red? That would be that not all cars are red. It's actually easy to show that all cars are red is false, right? Because all I need to do is go out to the DV student parking lot there and find one car that isn't red. And then I can say, well, okay, see, that evidence means that I can clearly show, I can reject that hypothesis that all cars are red. So it turns out that it's much, much easier to reject a hypothesis than it is to prove a hypothesis. And so in this class, we never prove hypotheses, we reject hypotheses, okay? All right, so in statistical analysis, we usually believe something is true, right? We have some reason to believe something's true and we're investigating it. But what we do is we start by assuming the opposite, that what we believe is true is not true. And that opposite statement is called the null hypothesis. So we go ahead and assume that that's true. And then that means that what we originally believed was true is a different hypothesis. And so the name for that in statistics is the alternative hypothesis. So the alternative hypothesis is what we're trying to show is true or not, right? And then the opposite of that is called the null hypothesis. So what happens is if we're trying to show whether or not the alternate hypothesis is true, the thing we're showing, we first ask ourselves, what would the opposite be? And once we've established that null hypothesis, we look at the evidence and we say, is this evidence convincing enough for us to reject that null hypothesis? Or do we have to fail to reject that null hypothesis? Because all we can do is either reject it or not reject it. Okay, and then the idea is if we can reject the null hypothesis, then that gives us enough information to say we believe that the alternate hypothesis is true. So if you reject the null hypothesis, you're saying the alternate hypothesis is true, which is what you were trying to prove in the first place. And that seems kind of convoluted. Why would we go through this? And the reason we do this convoluted kind of reasoning and logic is because of how difficult it is to prove something's true, but how easy it is to show that something's false. Okay, so let me give you some specific examples here. Okay, they're all going to follow this general pattern, right? We're going to have two possible explanations for a scenario, right? The noteworthy situation that we think might actually be true, that's what we're going to call the alternate hypothesis here. HA is the abbreviation for that. H for hypothesis and A for alternate. HA is what we think might be true. But what we have to do is think about what's the opposite of that. What if it was actually true that that noteworthy situation is false? That's called the null hypothesis, and it's written HO or H0. Right, you can think of it this way. The null hypothesis is the dull hypothesis. It means no, nothing to see here, move along, nothing noteworthy going on. It means everything, the status quo is what's true. Okay, then we consider our evidence, which is something taken from a sample typically. And if we're going to say, let's assume that the null hypothesis is true, and let's determine based on how unusual our evidence would be, if that's true, whether or not we can reject that null hypothesis. Okay, and then in the end, we're going to make one of two conclusion paragraphs, and they always look exactly the same way. So let me go ahead and start showing you the wording, the way we need to write it up. If the evidence we have supports rejecting the null hypothesis, then we first make a sentence that says we reject the null hypothesis. And then we have a second sentence that says we therefore do have sufficient statistical evidence to conclude the alternate hypothesis is true. On the other hand, if we look at the evidence and that does not support rejecting the null hypothesis, then that means we have to say in the first sentence, we fail to reject the null hypothesis, and in the second sentence, we do not have sufficient statistical evidence to conclude HA. So this is a little easier to understand this template if we look at three specific examples. Okay, these are made up, but they're good for illustrating the ideas. Okay, let's start with that one, that ridiculous one we said. Let's say that we think that all cars are red. Okay, well, there's two possible things that can be true, right? Either all cars really are red, which we're going to call our alternate hypothesis, HA, or the opposite is true, that not all cars are red, and that will be our null hypothesis. So we're going to look at our evidence. So we're going to assume that the null hypothesis is true. We're assuming that not all cars are red, okay? And then we're going to consider the evidence and decide if we can reject that. So we're assuming that all cars are not red, not all cars are red. And it looks like I have a typo in the notes here. We're assuming that all cars are not red. We assume the null hypothesis is true. And then we go out in the parking lot and we see a white car, right? So the question is, what can we say about this hypothesis? Okay, so we saw a white car, and that means that the hypothesis not all cars are red seems like it might be true, right? Because we have evidence that says that, oh, well, we certainly can't reject this, right? Remember, the only thing we can do is reject or not reject a hypothesis. We can't show that it's true. So what we would say is, in this case, the evidence does not support rejecting this. We can't say that it's not true that not all cars are red, because a white car, it kind of supports this idea. So what we would say is we fail to reject the null hypothesis that not all cars are red. Therefore, we do not have statistical evidence to conclude that all cars are red. Okay, now that seems really convoluted, the wording of that, but what this will get easier to you as you practice it and see more examples. And by the time we get through this unit, this will be second nature to everybody, just as long as you are careful at the beginning to get it right. Okay, let's look at some other examples that may be a little bit more realistic. You remember earlier, very early on, actually the very first day of the course, we considered an example problem about pilots that were going for captain's positions. And we had a sampling of a bunch of pilots, and then some of them were males and some of them were females. And there were a certain number of openings. And it turned out that of the 8 openings, or I think there was 8 slots for captains, 5 of the 8 went to women pilots, even though there was less than half of the group of pilots were women. And so there was what we were wondering if there was hiring discrimination. And if you remember, what we did is we did a simulation where we all tried different. We assumed that the lottery for selecting the captains was fair, and then each of us did a simulation to just randomly select pilots, and then we counted up how many times we got 5 or more of the pilots that were selected were women, and we did a dot plot to kind of show the distribution. This is sort of like a sampling distribution model of what would happen, right? And then we said, well, how likely would it be that we would have 5 or more? And it turned out that 12% of the time we did have that happen. So we concluded it wasn't that unusual. And because it wasn't that unusual, it means that we can't really say that there was hiring discrimination. It could have just happened randomly. Okay, so let's put all of that in the scenario with hypotheses. So this is the way we would do this. If we start with the thought that maybe the lottery used was not fair and favored female pilots, that would become our alternate hypothesis, that the lottery favored females. So the null hypothesis would be that the lottery was fair. Nothing to see here. It's just the dull case. Anything that happens is just due to random chance. Okay, and so then we assume the null hypothesis is true. We assume the lottery was fair, and then we consider the evidence. So when we did conduct a whole bunch of fair lotteries, we found that actually about 12% of the time, this many captains would be females. So what happened in our case would happen naturally 12% of the time, and that's not unusual. So since that's not unusual, remember our kind of boundary for judging unusual is below 5% chance of happening randomly. then we said that means we can't reject this, right? This is not strong enough evidence. This is not unusual enough for us to say the lottery wasn't fair. So we would say the evidence does not support rejecting the null hypothesis, and we would write it this way: we failed to reject the null hypothesis, therefore we do not have sufficient statistical evidence to conclude that the lottery favored females. Okay, so this is the structure that we use for writing up a hypothesis test. And we'll get into the details of this percentage calculation more a little bit later. Just trying to get the general flow of way hypothesis testing, this weird negative of a negative logic works. Okay, one more example. This is not numerical, but just to serve as a point. Let's say that a person has been arrested because the police believe that they've committed a murder. Okay, so there's two possible explanations for that. Either the person is guilty, right, which would become the alternate hypothesis, or the opposite of that, the person is not guilty, becomes the null hypothesis. Okay, so then we consider the evidence. We assume the null hypothesis is true. Innocent until proven guilty is the idea, right? So we assume, let's say we assume the person is innocent. Then the prosecution presents a bunch of evidence to try to say, okay, well, this is why I think you should reject that idea that they're innocent, right? Let's say the prosecution provides the following evidence: the bullets matched a gun that's owned by the person. Okay, sort of convincing. And then their fingerprints were the only ones on the gun. Okay, a little more convincing, although somebody could have, used gloves when they used this defendant's gun. But then let's say also there's a video that shows that the person is shooting the victim with a gun, so they're caught in the act. Okay, well, in that case, the evidence is pretty overwhelming, and that would have to say that the evidence supports rejecting this hypothesis. We can no longer support that the person's not guilty when we have a video showing them committing the murder. Okay, so in this case, that means the evidence does support rejecting the null hypothesis. So we would say we reject the null hypothesis, therefore we do have sufficient evidence to conclude that the person is guilty. All right, so that's how it works, either to conclude that the alternate hypothesis is not true, or in this case to conclude that the alternate hypothesis is true. And this is the standardized wording for that. All right, so here's all three of those things side by side. Let's look at a couple things. The first thing to notice is that we're always rejecting or not rejecting the null hypothesis, right? We're using evidence to judge, what do you think about this? Is this true or is this not true? Can we reject that, or do we fail to reject that? Okay, we're never favoring or proving anything about the alternate hypothesis. We're always evaluating something compared to the null hypothesis. The first sentence in the write-up is always about the null hypothesis. We either fail to reject it or we reject it. That's it. And then the second sentence in the write-up is always about the alternate hypothesis, and it always includes the context wording like that. Okay. The other thing to notice is that in the two sentences, the two sentences either are both negative words or both positive words. So we fail to reject the null, therefore we do not have sufficient evidence to conclude the alternate hypothesis. Or we do reject the null hypothesis, therefore we do have sufficient evidence to conclude the person is guilty, or the alternate hypothesis. Okay. So we'll see that through as we do more examples together. Okay, the next thing we're going to talk about is this 12% value. Now, normally we calculate this like for the pilots, we did this with a simulation, but we went through a whole probability unit in first semester specifically so that we wouldn't have to resort to simulating things to try to get this, right? And we also, in chapter 18, figured out how things like p-hat values should vary from person to person, so that, or from sample to sample, so we can use probability to determine how unlikely something is to occur, right? So we have this thing called the p-value. So what is the p-value? Well, p-value stands for probability value, and that p-value is the probability that if you assume the null hypothesis is true, then the evidence would be this far away from what the null hypothesis is saying, just due to natural random sampling variation. In other words, the likelihood that what happened in the sample would happen by random chance if the null hypothesis is true. Okay, and the p-value is the probability that allows us to judge how unusual a result in the sample would be. Any p-values that are below 5% are considered unusual. Any p-values that are above 5% are not unusual. Okay. And so if a p-value is unusual, below 5%, that means that it's so unlikely to occur that our assumption about the null hypothesis being the center of the distribution for the sampling distribution is probably wrong, so we reject. So low p-values are unusual and they are linked to rejecting the null hypothesis, okay? High p-values above 5% are not unusual, and therefore we fail to reject. They're not unusual enough for us to reject where the center of the distribution is. In other words, we have a distribution here for p hats, right? And we know that these p hats are around here. And these are centered at whatever are what we call p0, the null hypothesis value, okay? If we have some particular p hat and it's way out here, let's say, that's maybe the p-value for this would be something like 0.002. It's like 0.2% of happening randomly, like shading out here is way down, right? So that's unusual. And if that's unusual, that means that we would reject this null hypothesis because this can't be the center. That can't be the center if we have a sample way out here. The sample's probably maybe, or the center's maybe up here where that would be more likely to occur. So that's why low p-values are associated with rejecting the null hypothesis. We're rejecting that the center could still be there if we get too unusual of a result, right? On the other hand, just to illustrate the opposite of that, let's say that we had that distribution of p hat values and centered at our null hypothesis value. We have all these different p hats that could occur. And maybe in our sample, we happen to get this one right here, okay? So the p-value for that might be really high. Like the p-value, the probability value of that happening might be 0.42. There's a 42% chance of that happening, that p hat happening just by random chance. So that means that's not unusual. And since that's not unusual, then that means we're not going to reject that this is the center. This could definitely still be the center, right? Because that's not unusual to happen. We expect that to happen even if the null hypothesis is true. Okay. All right. So that's what the p-value means. It's the probability of the sample's value happening if you assume the null hypothesis is true. So how do we calculate it? In the red cars and the person is guilty example, really didn't quantify anything. There wasn't a p-value. But in the female pilots and captains example, we conducted a simulation to imagine what would happen if we had a lot of cases, right? This allowed us to evaluate what did happen, which we're going to call the evidence in comparison to all the outcomes that might have happened, right? And we did that with a simulation, right? But instead, what we're going to usually do is if we measure the evidence as a mean or a proportion from a sample instead of a simulation, we can use chapter 18 methods to figure out the sampling distribution model. And then we can use normal CDF to calculate the probability in that sampling distribution model of a value being this far away from expected. Okay. All right, so let's take another example a little closer to home. This is all made up just for the purposes of illustration, but just to try to put it in context, that's stuff that's easier for us to identify with. Okay, suppose that DV counseling department records showed that in the past, 78% of the seniors at Desert Vista stayed in state for college, went to one of the in-state schools. So we ask a simple random sample of 40 seniors this year whether they plan on staying in state. And suppose that 34 of them, which is 85% of them, said they are staying in state, right? Historically, it was 78%. This year, it's 85%. Do we have reason to believe that more seniors are staying in state? Well, definitely this value here, which would be our p hat value in our sample from this year, it is higher than what we've seen historically, right? So to determine if that's really unusual, we're going to say, let's let the null hypothesis percentage be the historic value, 78%. And let's see whether or not this value is unusual. Okay, so the way we'd write this up first is we'd state the hypotheses. And I'm going to ask you to do this both symbolically and in words. I'll show you what I mean. And we'll always define symbols too. So we'll define the symbol P to be the percentage of DV seniors that are staying in state for college. That's a proportion. Okay, and so the null hypothesis, which you don't have to write the word null hypothesis, but HO, is going to be that the percentage of people staying in state is 78%. And because we're evaluating something for the whole population, these are always population values right? So they always use parameters, right? So you don't ever use p hat here. It's got to be p because we're evaluating something at the population level. For the entire population, right, we're going to make the assumption that that the proportion is still 78%. Remember, the null hypothesis is the dull hypothesis. The dull situation would be nothing's changed. This year's the same as last year. 78% of DV seniors should still be staying in state for college. Okay, so symbolically we could write that as p equals 0.75, and in words I could write 78% of DV seniors stay in state for college. Okay, so the alternate hypothesis, this is what we're investigating. What we're investigating is based on this wording. Do we have reason to believe that more seniors are staying in state this year? So if more were staying in state, then we would say HA, the alternate hypothesis, is that the population percentage that are staying in state is now greater than 0.78. Not that it's equal to 85%, just that it's larger than it was historically. And in words, we would say that more than 78% of DV seniors are staying in state for college. So this is the way we would write. This right here is the way we would write the hypotheses for this problem, and we would define our symbol like that. Okay, so the first thing we always have to do is state hypotheses. Okay, a couple things to note. The null hypothesis case is always equal. Okay, and it always equals the status quo value or the dull value. The alternate hypothesis has to either be greater than, or we'll talk about other cases there. This value here is always the same as this value, right? We never use two different values here. And this symbol is always the same, and it has to be a population parameter symbol. Okay. All right, the second thing we have to do is check conditions. And the reason for this is we're going to calculate the p-value by using a normal distribution. So we have to meet all the criteria for Chapter 18 sampling distributions in order to do this. So the conditions are that we have an SRS, or that we believe we have a sample that's representative of the population. So we would state that the problem says that a random sample was taken, and that's how we would know that that condition's met. We have to believe that the samples are independent, assume the samples are independent from each other. In this case, we don't know, so we're going to state that we're assuming that the students in the sample were independent from each other. In other words, we didn't take a bunch of people who were all in speech and debate, so they might be going to similar colleges, for example, something like that. It's just a random sample of seniors from the whole school. Okay, we have to meet the n is less than 10% of the population criteria. 40 is definitely less than 10% of all DV seniors. And then we have to have a big enough sample to say that the shape of the sampling distribution is approximately normal. So n is 40, p is the population value, the null hypothesis value. So now this is important. When we do the conditions here in Chapter 19, when we check conditions, we always use the p hat value because everything was centered here. But in hypothesis tests, we're always centering at our assumed null hypothesis value. So we use the null hypothesis value for this. So 78% of 40 is 31.2, and the other 22% of 40 is only 8.8. This one's actually a little bit too low. It's supposed to be at least 10. So technically we don't meet this criteria, okay? And that means that our shape might be slightly different from a normal shape, okay? So we're not going to let that stop us, but we're going to note that we don't quite meet conditions. And I'll show you how to handle that at the end. We don't allow not meeting conditions to stop us from doing the problem. So first we write hypotheses, then we check conditions, and then we conduct the test. So here's how we do this by hand. First of all, from our SRS, we had that there were, what was the value? It was 34 out of 40, which is 85%. So we calculate this, 34 out of the sample of 40 is 85%. That becomes our p hat value, okay? And then we say, okay, if we were to compare how much p hat would vary from sample to sample, what would we see? Well, we know that this is going to align itself with the population value. We're currently assuming that that's 78%. So we're going to put that as our mean. This is a sampling distribution model for p hats. Okay, and then we have to calculate the standard deviation. So that's going to be, we look at the formula for a proportionate square root of pq over n. And so that's going to be the square root of p, which is 0.78. Let's see, times q. Get the worked out result here, which is 0.22. And then the sample size in this case was 40. So that turns out to be 0.065. So that's my standard deviation. Okay, this is how I'm expecting p hats to vary from sample to sample. Right? If I took a different sample of 40 students, I'd have a different p hat value, maybe not exactly 85%. But what I'm evaluating now is how unusual is this particular value. Okay, so to do that, we're going to say, all right, now that I've got my labeled sketch here for the sampling distribution model for p hats, let's look at that particular p hat value, 85%. Since we're evaluating a hypothesis that the percentage has specifically gone above 78%, we will shade to the right of that boundary, this shading here, and then we're going to use a normal CDF function to evaluate it. So we would say this is equal to normal CDF from 0.85 is the lower boundary, labeled lower, to infinity, or 999 for the upper boundary. If the mean was 78%, that's the mean labeled, and the standard deviation is 0.065, right? And then we do that in a calculator, and we end up getting that it is 0.14, okay? This value here is called the p-value, not to be confused with p for the population value. It's unfortunate they both have p's, but that's why in this course I always write it p-value to keep it separate from p for the population. What that means is if this year's population, the percentage of seniors staying in state is still the historic 78%, there's a 14% chance of us having our 85% in our sample just due to chance, right? And that's not unusual, right? This is not unusual. Remember, we said it would have to be less than 5% chance for it to be considered unusual. Okay. All right. So because it's not unusual, we can write our conclusion paragraph. Well, since it's not unusual because it's above 5%, that means we're going to fail to reject the null hypothesis because it's not unusual enough for us to reject this. We can't reject this. We think this is okay. And therefore, we can't conclude that it's changed. So this is the way the paragraph would look. We have to say it just like this. With significance level of 0.05, we have to tell in the problem, in the conclusion paragraph, what is our boundary for determining whether something is unusual. The p-value of 0.14 is high. It's just above 0.05. So we fail to reject the null hypothesis. Okay, the first sentence is written just that way. Indicates significance level, p-value, and our result. Do we reject or fail to reject the null? Because we failed to reject the null hypothesis, we do not have sufficient evidence to conclude that more seniors are staying in state this year compared with previous years. What we're saying is, this is the history value. This is this year. Okay. And yeah, this year's a little different, but that difference would happen randomly by chance enough to where we don't consider that unusual. So this evidence is not strong enough for us to say that the alternate hypothesis is true, right? Going back to the hypotheses, right? We said, given that that this is true, there's a 14% chance of us having 85%. So we failed to reject this. We still think this is true. But the way we say it is, we do not have sufficient evidence to conclude that more than 78% of the seniors are staying in state. And that's it. That's how a hypothesis test is done. We state the hypotheses. We check conditions to make sure that we can use a normal curve. Then we conduct the test by figuring out where the mean and standard deviation is for the model that models how these p-hats move around. And then we calculate the p-value by using the samples value as a boundary and determining how unusual it would be to occur if the null hypothesis value was true. And then we use the p-value to either reject or not reject the null hypothesis to write the conclusion paragraph. That's it. All right, I know it seems overwhelming and really convoluted, and it will for a while, right? But I guarantee you, if you steadily work and practice, it'll get to where this is all second nature, right? It seems weird at first, but it becomes more natural over time. Okay, so the steps for conducting the hypothesis first, just to review again, state the hypothesis, both symbolically and in words, define all non-standard symbols, check conditions, do the test to find the p-value, and then write the conclusion paragraph. The first sentence is always in terms of the null. Second sentence is always in terms of the alternate in context. Okay, now we noted that there was a problem, right? One of our conditions wasn't met. So if that happens, then you tack on another sentence to the conclusion paragraph. You say, however, the sample size is slightly too low to meet conditions for inference, so we may not be able to trust this result. We go ahead and write it up, but we can tack on a sentence and say we're not super confident. The reason why is our sample size was a little too low, so we made the assumption this was a normal curve. But what might have happened is it might be a little skewed. So our p-value calculation might be a little bit off. It's not like we can throw this out, but it's not as trustworthy. Okay, and then there's one last thing I want to show you, and that is that just like for the confidence intervals, there's a calculator way to find the p-value in a single step. It's called a one prop z-test, one proportion z-test, just like the one prop z interval does the confidence interval. So if you pull up a calculator and you go to, let's see, stat, and then over here to tests, there's going to be a one prop z-test. It's number 5 here, one prop z-test. And then you have to enter the p0 value, the null hypothesis value. So in this case, it would be 0.78, because we're assuming 78%. You have to enter it either as a fraction or decimal. And then you have to put in the actual number of successes, which in this case was 37 out of the 40 students said they're staying in state. And then you have to indicate the direction that we're shading. We're shading to the right. So we're going to go over here to the proportion is greater than the null hypothesis. We'll explain the next video why we use these other ones. And then we can do the calculation. And the calculation will give me the z-score for that value. And then it'll give me this p-value here. This is the p-value, 0.013. We calculated it as 0.14 because we had a little bit of rounding here. Or sorry, 0.013. Wait a second, why is that so different? Let me, there's a discrepancy here. Let me do this by hand just to verify what happened here, because I think I must have a typo in my notes. If we do normal CDF with 0.85 from the sample to infinity, if the null hypothesis value is 0.78 and 0.065 is the standard deviation, the p-value is 0.14. So I must have made a mistake when I entered something in here. One prop z test, stat tests, one prop z test. Is that the right one? Test, one proportion. Yep, that's right. 0.78, 37 out of 40. Oh, that's why. I have the wrong number here. It wasn't 37, was it? It was 34. That's why. That's where the typo is. Sorry for the confusion. This needs to be a 34 because that's what we actually had in the problem. Okay, let me do that right now. Okay, yeah, there's the 0.14 number. Okay, so typo in the notes. This is 34, not 37. All right. Okay, let's do one other quick example. Let's just change the problem up slightly. What if we had 37 instead of 34 seniors that said yes? That means that the p hat value would go up to 92.5%, which moves our p hat value further out, which means that the p value should be lower. In fact, nothing would change about our hypotheses or checking conditions. But when we got to the part where we calculate the p-value, since this is so much further away, more standard deviations away, the chance of that happening randomly is only 1.3%. So the p-value drops. So this boundary value is changing for each sample. Okay. And then that means we would change our conclusion. We'd say 1% is unusual. It's not likely, right? It's so unusual that it causes us to reject the value for the null hypothesis. It causes us to put in question, is it really true that 78% of people are still going to state schools at DV, right? Because this is too unusual now for us to not reject the null hypothesis. So because this is less than 0.05, we are going to reject the null hypothesis. So the way we write this up this time would be, with a significance level of 0.05, the p-value of 0.0013 is low, so we reject the null hypothesis. Therefore, we do have sufficient evidence to conclude that more seniors are staying in state this year compared to previous years, right? What we're basically saying is this can't be true. So the real value for P is probably somewhere higher than that, because it has to be somewhat higher so that this becomes not unusual. That's the logic of it. All right. All right, at this point, we can do one last thing, which is required practice number 1, and then that's going to finish off the first day. Usually at this point, I ask students to go ahead and work this on their own. So what I'm going to ask you to do is to pause the video, go to the required practice packet, and try number 20. Practice packet 20, try number 1, the first problem on the chapter 20 required practice packet, then unpause the video. Okay, let me go ahead and go over this. We may or may not actually do this in the actual class, but depending on the time, I'll go ahead and go through it now because I might be referring people in the live class to this to get the solution. The first one says congenital abnormalities. All right. In the 1980s, it was generally believed that congenital abnormalities, that means birth defects, basically, people that are born with things that are not normal compared to the normal population at birth, that these affected about 5% of the nation's children. Some people believe that the increase in the number of chemicals in the environment has led to an increase in the incidence of abnormalities. A recent study examined 384 children and found that 46 of them had a sign of an abnormality. Is this evidence that the risk has increased? Well, let's just first take a look at that. So the p hat would be the percentage of people who have abnormalities. In this case, it was 46 out of 384, right, in the sample here. So if I do 46 divided by 384, that turns out to be about 12%. I'm just going to round that to 12%. So that's 12% when we normally expected, historically, it was 5%. So the evidence is definitely that there's more abnormalities now than before. The question is this high enough for us to consider that something has changed? Okay, so the first thing we're going to do is we're going to state hypotheses, right? So the first thing we're going to do is say, well, what is it that we're checking? I'll do this both in symbols and in words. So the null hypothesis, the alternate hypothesis. So the alternate hypothesis is there evidence that the risk has increased? So that means that we're going to have P, the proportion, is something greater than the historic 0.05. And in words, we could say a higher percentage of children have abnormalities. Okay, so then from that, which comes from the wording in the problem, we're going to say, well, what the opposite would be. The opposite would be if there's no change, right? So the null hypothesis is the dull hypothesis, means that we still have 5% of children having abnormalities, that the percentage of children with abnormalities is still the 5% that it's always been. Okay, so the null hypothesis means nothing to see here, nothing's changed. And that, for that to be true, it means that this difference would have to be not very unusual. Okay, if this difference is unusual, this much of a shift, then that means that the alternate is true. So next thing we have to do is check conditions. So the first condition is we have to have a simple random sample or believe that the sample is representative of the population. It says a recent study examined 384 children and found that 46 of them showed an abnormality. It doesn't really say how that was collected, so we're going to assert that we're just going to assume that the sample is represented. Sample is representative. We always have to state a reason why we think a condition is met. Okay, we also have to have independence from child to child. Again, we're going to assume that this is true. Okay, then we have to have a sample that's not too big, so it has to be less than 10% of the population. What you should do here is write 384 is less than 10% of, and then identify what the population is of children. 10% of children. That's definitely true. And then we have to show that NP is at least 10 and NQ is at least 10. So NP would be 12% of 384. That's the 46 number. And NQ would be the other, let's see, 100% minus 12% is 89, or 88%. The other 88% of 384, that would be, let's see, we had 384 and 46 of them are the yes case, so 338 are the no. Both of those are greater than 10. And what that's telling me is that we can assume that the sample is a representative of the population and its model is normal. Okay, so all the conditions for inference are met. The next thing is we'll conduct the test, and we're going to do it by hand, but then we'll check it in the calculator. Okay, so to do it by hand, first of all, I'm going to figure out what the p-hat value is. And I think I did this above, but 46 out of 384 is 0.12. And then I'm going to figure out what the standard deviation is, right? The standard deviation is the square root of p, which is 0.12, times q, which is 0.88, divided by the sample size of 384. And if you plug that in a calculator, you get 0.011. So then I'm going to use that to make a sketch for p-hat values. Okay, they're going to be centered at the null hypothesis value. And the null hypothesis value here is going to be the 5%. Right? We always center everything at the null hypothesis value. The standard deviation we just calculated is 0.011. And that allows us to judge whether or not our sample is unusual. So our particular p-hat value was 12%. So up here above here, there's somewhere out here is 12%. That's the p-hat value. And because my hypothesis value, my alternate is greater than, I'm going to shade above this. And then I'm going to use a normal CDF function to compute that, right? That's going to be that the lower value is 0.12, labeled lower, to infinity, labeled upper, with a mean of 0.05 and a standard deviation of 0.011. And that's going to turn out, let me label this the p-value, is going to be equal to, well, if you do it on a calculator, let me just show you what happens. So 0.12, because so many people make an error here, 0.05, 0.011. Okay, so that says 9.9 e negative 11. This means times 10 to the negative 11th. Okay, some people will write that this is 9.9. That's not right. It's 9.9 times 10 to the negative 11th. What that is 10 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 9, 9. It's extremely low, right? In other words, very unusual, okay? And since it's so unusual, it means that this difference cannot just be due to chance. We're going to have to reject this, right? Okay, just to check our p-value, let's just try it in a calculator. And if you later, I'm going to show you how you can write this up. But for now, we're just going to use this for checking. So if I go over here to tests and I do a one prop z test, and I say the null hypothesis value was 5%, have birth defects here, and then we had 46, was it 46? Yeah, 46 out of 384. And then we're shading to the right here. Let's do the calculation. Yep, p-value is slightly different just due to rounding, but it's 1.7 times 10 to the negative 10th. So it's extremely low, almost zero. So we're good. Okay, but the important thing is we want to write the conclusion paragraph. So let me write that up. I'll use a text tool for that. With significance level of 0.05, meaning that's where we're going to judge if something's unusual, p-value equals 9.9 times 10 to the negative 11th power is very low, so we reject the null hypothesis. We're going to reject HO. That's the first sentence. The second sentence is going to be, since we did reject the null, that means we do have sufficient statistical evidence to conclude, and then we write whatever our alternate hypothesis wording is, which is that a higher percentage of children now have abnormalities. With that, maybe we can say this: the percentage of children with genital abnormalities is greater than the 5% historical value. Now, we can't make any conclusions about whether that's due to chemicals in the environment because we haven't conducted an experiment, but we can say that that change from 5% to 12% is definitely statistically significant. All right, so that's how we write up the result. All right, that'll be it for this video, and then we'll have other parts to cover the rest.